Hi, my name is Marielle Von Stein, and this is the video submission for Steering the Future, a catalog of failures in deep learning-enabled robotic navigation systems, under submission to ICSI Demo Track 2025. We've all seen ground robots fail in a variety of ways, some entertaining, some truly terrifying. In many cases, the software of these systems is scrutinized and often blamed as a prime cause of these failures, in particular, machine learning software. The software engineering community has a plethora of techniques for detecting and addressing failures in software systems. Notably, runtime monitoring constantly observes the executing software and looks for some property violation that is of interest to the end user. And fault isolation aims to narrow down the potential causes to expose the root cause of the failure in hopes it can be more clearly understood and, eventually, fixed. The software engineering community has designed several similar techniques with robotic systems in mind. Self-Oracle performs out-of-distribution runtime monitoring and simulation, but has significant limitations to its generality and applicability to real data. DeepRoad is an open-loop fuzz tester using GANs to introduce style transformations that mimic inclement weather and expose accuracy issues that may not translate into system-level failures and do not reproduce real data faithfully. And DDENV can perform fault isolation by narrowing down to a one minimal environment that still reproduces the failure of interest, but this is difficult to translate beyond additive simulated environments. In summary, software engineering for robotics projects lack in a few key areas. They do not test on real systems because they are expensive in terms of time, resources, and expertise. The simulation or static real data limits the generality of the technique, and reproducibility in comparison across techniques is stunted by the heterogeneity of the systems that we do test on. In general, our community could benefit from studying a readily available real system. Our repository, Failures for DeepNav, will serve as a critical resource to lower these barriers to improving software engineering techniques for robotics. This project provides setup instructions for the commercial, off-the-shelf Robotic XL with Intel NUC onboard computer, Z2 stereo and depth camera, RP LiDAR sensor, Mecanum or normal wheels, plus many more available extensions. We also provide a codebase for data collection, training, and deployment, as well as a number of pre-trained navigation models and a catalog of real-world failures that correspond to those pre-trained navigation models. One such failure is shown here, on a Dave 2 with dropout between fully connected layers. As we can see, the robot performs well, navigating the hallway until it reaches a student seating area full of students that were not there when the training set was collected. The Robotic wavers in its trajectory and then ultimately crashes into a seated person's foot at the left-hand side, which we can see reflected in the angular speed predicted by the DNN. Another unique failure came from the deployment of a transformer VIT-8 backbone with a linear trained head. Again, the model performs well until it comes across an open office door that was not in the training set, zigzags, and then crashes into the left-hand wall. And that behavior is reflected in the DNN predictions at the end of the trace. Our catalog, Failures for DeepNav, lowers the barriers to study, generalize, and compare software engineering failure analysis techniques on robot navigation systems. We provide a fully documented codebase to collect data and train an end-to-end deep learning navigation system for a popular commercial ground robot, a growing catalog of dozens of pre-trained deployed navigation models, and thousands of traces for successful and failing runs. We hope that you'll check out our tool at the GitHub link below or by using the QR code, and thank you so much for your attention.